Okay, now that we introduced the law of electromagnetic induction, there is a concept that follows from that. There is this concept of inductance, there is the concept of mutual inductance, and there is the concept of self-inductance. This concept of mutual inductance and self-inductance, falls together with one of the four most important elements of electricity and electronics. Okay, so recall that in electricity and electronics, there are four basic devices, and which we have already covered. The first one that we covered, not all four, we covered only two of them. The first one and the simplest one is the capacitor. It's an old device. Then I introduce you to resistor. And now I am going to introduce you to a device called the inductor. And there is one more device that we are not going to cover in this course. That's called the transistor. Okay? Everything related to electronics that we have is a combination of those four devices. Everything. You combine them in different ways and you get different devices that perform different functions. Okay? Everything, every device, every gadget, right? Every electronic gadget that we have out there, is a combination of these three basic devices. So we talked about the capacitor, we talked about the resistor, and now we're going to talk about the inductor. The capacitor here, is a device that's related to electric charges. This device here is related to electric current. And this device here is related to the magnetic field. Okay, this one is more complicated, we're not going to cover, so we're going to leave it this way. Okay. So how do I introduce you? Because we have this phenomenon of electromagnetic inductance, right? Electromagnetic inductance. We can come up with a device related to this phenomenon, to which we give the name of inductor. Let's see how and by the way, not only we have the device called the inductor, but we also call that the inductor has a inductors have an inductance, right? By the same token that a capacitor has a capacitance, a resistor has a resistance, then an inductor is going to have a inductance. So let's see how we define the inductance of an inductor, right? But again, before we get into that, let me do one more thing. I want you to remember how do we define the capacitance, right? Capacitance is the charge divided by the voltage. Which, by the way, we can rewrite that in terms of the V. V is going to be the Q divided by C, or even better, I'm going to write in a better way. Instead of Q divided by C, I'm going to write 1 over C times Q. Okay? There's a reason for that, and you're going to understand why. And then, for a resistor, what do we have? We have something like that. V equal to Ri. Okay? Notice that here we have the charge, and here we have a current, which is nothing but dq dt. Okay? And now I'm going to put them side by side. Okay, here we go. Okay. So you can visualize it better. And then we're going to go for the next step. That's, let's see, the voltage, right, across a capacitor, the voltage across a resistor. And then what we're going to do, we're going to come up with an equation that's going to provide us with the voltage, across an inductor. The inductor we abbreviate by the letter L. Let's see how it looks like. But before we get in there, again, notice we have something here that's related to the geometrical parameters of the device times an electric charge. Here too, we relate a quantity that's related to geometrical parameters of the resistor, right? The area, the length, plus the intrinsic property of the device, times, not a Q, but a dq dt. What about the inductor? What are you going to get for the inductor, right? Before we do that, let's consider what happens when, when we get two devices together, two coils together. What happens when we get two coils together? One connected to a generator, just like the one we described before, and the other in close proximity we get two coils together, one coil or solenoid connected to a generator, and the other in close proximity to the first one. Okay? So that's the illustration that I have here. Here you go. That's the symbol of the generator. Okay, the stewed here represents that the current, the voltage is changing in a sinusoidal fashion. So what do we have here? We have current flowing back and forth throughout all those wires. Okay, and while it does that, all this current is generating a magnetic field that's switching back and forth. Can you picture that? If this guy is not a generator, it's a regular battery, right? Suppose that this guy is a regular battery, the magnetic field are going to point just in a single direction. But because it's a generator, the magnetic field is still going to have a uniform distribution, the cross section of the coil, of the solenoid. However, the magnitude of the field is going to change back and forth. It's going to Sometimes it's going to point to the left, then it's going to point to the right, to the left, and to the right. And all the magnitudes of the magnetic field at each instant of time is going to be uniform. Okay? Simple enough? So when we introduce a second solenoid inside the first one, just like I did here, what's going to happen? This first solenoid will induce a current in the second one. Notice that the second solenoid has no power whatsoever. Okay? So we start, like the following. We continue like that. What happens right now? The first solenoid is connected to the generator, right? I'm going to repeat it here. Solenoid is connected to a generator. The second solenoid has a smaller radius, and is inserted into the first solenoid, just like the figure indicates. Oh, by the way, this second solenoid has no power of its own and is a closed circuit. Okay? And the first solenoid has an electromotive force okay, I'm going to use this one here. Has an electromotive force that can be expressed like the following. Omega t. Now if I want, I can introduce a phase constant here. Okay, phase constant here, and I'm going to put like I want to specifically state that there is the first solenoid. That would be the best way. Let's see what happens. Right? This first solenoid, of course, has a resistor, right? And the current is going to be given by this value right in here. Don't forget that this current now is a function of time, right? This current now is a function of time. Because this current is a function of time, and let's put that here. I'm going to specify the first solenoid, the primary solenoid. Let's not forget that the magnetic field inside this first solenoid is also going to be a function of time. And why is that? Because it's a function of the current, right? Here you go. And now, whoa, right? Because the first solenoid has a current as a function of time, it will also have a magnetic field as a function of time as well. And once we introduce the second solenoid into the first solenoid, there will be an induced current in the second solenoid, right? This smaller radius. So let's write it down. What's going to be the electromotive force induced in the second solenoid is going to be what? It's going to be the following. Epsilon 2 is going to be given by, we are going to use Faraday's law. And I'll call this one, this guy has N2 terms. Okay? And okay, I'm going to put the flux here. Magnetic flux. Because the magnetic field is not dependent on the position, we can go ahead and write down that the magnetic flux is going to be B times A. And by the way, it's going to be the magnetic field of 1 times the area of 2, because that's what's going to be the magnetic flux through the second solenoid, right? I don't even have to write the integral here because the magnetic field is uniformly distributed. Okay, and now let's write down my B1 here inside. And I will keep A2 like that. Assume that we know what's the value of A2. The area of the second solenoid is constant, it's not changing at all. So everything that's constant can be taken out of the derivative. Okay. And you can see, let's finish this equation. You can see that the electromotive force induced in the second solenoid is going to be a cosine omega right here. That's what's going to be the electromotive force induced in the second solenoid. Okay, we're going to here write all that. You can picture that, right? We can here write that in a different way. And how do you rewrite? I go back to what I see here. And you're going to see the nice relationship that you're going to get. Okay. What I did here, instead of writing all the stuff here in the place of B1, I'm going to write just this one here. Okay. Like that. To make it simpler. Okay. To make it simpler. And then you're going to see what an interesting result that we're going to get. Just like before, we are going to take out everything that's constant. We're going to take it out from inside the derivative. The area is going to be taken out as well. And we are going to be left with this derivative that you see here. everything that you see here, everything that you see here are related to the geometrical features of the device, right? Of the first and second solenoid, right? This little n here that you see is in reality number of turns in the first solenoid divided by the length of the first solenoid. Okay? And on the top of that, you have this derivative of I with respect to time. I didn't spell that out because I want to keep it in this format instead. Okay? Okay, so what we have here is the following. I'm going to write this equation, epsilon 2 what we have here is the following. I'm going to call this term here the mutual inductance between between coils 1 and 2. Okay? And note that we have now the electromotive force on one side, a constant multiplying a derivative. Now, let's put it together, right? Instead of writing epsilon 2, I'm going to also to write down V2 to make our notation consistent with the other two devices, right? Let's go back to my capacitor and my inductor. Notice that I put at VL, what VL is going to be, right? I just found out what VL is going to be. VL, or let's say the inductor number 2, is going to be given by a constant that is a function of the geometrical parameters of the device and multiplied to a derivative. Recall that this current is in reality a derivative of the electric charge, right? And look at the nice progression that we get here. I can even change the very first equation. And here, instead of putting V2, I'm going to put VL, the inductor. Okay? This term here, I'm not going to write down as Q. I'm going to write down in a better way. I'm going to write that in terms of a derivative, but I'm going to write in terms of a zero order derivative. In all those three cases, what do you have? We have that the electric potential difference of the device is equal to a constant that's related to the geometrical parameters of the device times a derivative of a given order. For my first the simplest device of all, for my first device that is the simplest of all, the capacitor, the derivative with respect to the electric charge is a zero order derivative that ends up to become a Q. For the next devices a little bit more involved, a little bit more complicated, we still have a constant that's dependent on the geometrical features of the device. Multiply it by a first derivative of the charge. And then we get to the inductor. Again, we have this parameter here. That's, again, the geometrical feature of my inductor multiplied by a second order derivative. Okay? So here, I hope you can memorize that easily. And that's a very important equation that we have here. Don't forget, this comes from Faraday's law. This comes from the so-called Ohm's law. And here is a definition of comes from the definition of the capacitance. Okay. What I exposed to you here, what I exposed here to you is the so-called mutual inductance. When we have two or more inductors, right, we end up with this type of relation among them. But what if we have just one inductor, right? If you have just one inductor, now we can start talking about self-inductance. With just a single inductor, we can start talking about another parameter that we call the self-inductance. How do we do that? Okay. We go back to our drawing, to our illustration. Not this one, but this one here. This is the single solenoid, okay? Single solenoid connect to a generator. The single solenoid has a current here, has a current that's changing in time, a magnetic field that's changing in time, and because it has a magnetic field that changes in time, it will affect its own original current. It's going to induce itself. You're going to induce a current on itself. That's why we call it a self-inductance. Okay? So you can write it down. For the case of a single inductor connected to a generator, the current will change with time, and there will be a B field that will change with time as well. This changing B field then will induce a current on itself, on this sole inductor. Then the name of self-induction. And let's see how it looks like. Okay? Going back to our drawing, this cross-section of our inductor has a magnetic field that changes in time. Consequently, there will be an induced electromotive force that is related by Faraday's law. Okay? So let's go ahead and write it down. Write it down. Just like before. Here you go. We have my inductor, let's say, with n turns, and the derivative of the magnetic flux. I'll keep it n right in here. And the B is still the B1, but now then I'm going to simplify to B because we don't need the subscript there. I'm just simplifying the notation. And the area is going to be the area of that specific inductor. Not just the magnetic field of that specific inductor, but the area of that specific inductor as well. Okay, and we do exactly the same thing that we did before. Instead of x, the A is going to be a constant, can be taken out of the derivative. The B We're going to do that in the next step, right? Not here. In the other step. This A here is going to be taken out of the derivative. Okay. And this magnetic field is going to be given by the equation of the solenoid that you are familiar with. We're doing that just for the solenoid. Okay, we didn't finish yet. We're going to take out all those constants that we have here. And di and differentiate with respect to t. And now we have this relation. Okay, I'm going to go one more step. This little n, what's this little n? Is the number of turns of the solenoid divided by the length of the solenoid. Okay. This n combined with the other n to become n squared. This n we do not need anymore, right? And just like I'm gonna arrange this b mu naught to be in front of here, and this a is going to be right in here as well. Okay. Just like before, we have what? Electromotive force that is a function of a universal parameter and a geometrical parameter of the device times the I dt. Okay? And that's the self-inductance. All this constant that you see here, oh, let's see here. I gotta change the, not to L, but I'm gonna put L prime here for the length of the solenoid because we use the L for something else. Everything that you see right in here, we give it a name. Not with the negative sign. Everything that you have right here, we give it a name. We call it not the mutual inductance, but the self-inductance. L equal to that. And my equation becomes simpler. L is the symbol for self-inductance. L di dt. Okay? This device is so important that we even give a unit, a special unit. You know, this parameter that you see here is so important that we even give a special unit to it, right? Let's line them down again. Okay, that's gonna be L12, right? Inductor 1, 2, and now I'll change my notation to V sub L or L di dt. We can come up with a unit for those guys, right? This one is unitless. This one has unit of meter. This one has unit of mu naught, of the mu naught and meter square, right? L and M the units of L and M this unit shows up so frequently that we give it a name of Henry for the letter H. Okay. I call that for the resistance. The unit of resistance is the ohm. and the unit of capacitance is the farad. Now that we have the relation for the electromotive force of the inductor, we can start talking about circuits that involve inductors, not just resistors, not just capacitors, but also inductors, okay? Circuits with inductors. The first circuit with inductors is the RL circuit. Resistance, a circuit with a resistor plus an inductor. Let's take a look how it goes, we can have something like that. I'm gonna show here, okay, right in here. It's a DC circuit, okay? Because we have here a regular power supply, and then we have the elements with the resistor and the inductor. We can have circuits with those solenoids that you see out there, okay? And by the way, that's a very important device, especially when combined with a capacitor. Let us study what happens, how this type of circuit behaves. The way we do it, we use Kirchhoff's loop law. We come up with a loop, right? And get the equation out of this loop. There is just one loop, no junction. The moment we close it here, the current is going to try to flow through this circuit. And how do we write the equations of this circuit? Okay, it's going to have a V. We know that the resistor loses electric potential. And then for now, I'm going to put V sub L for L. And all of that is going to be equal to 0. That's the equation that I have for my resistor. What we're going to do, find the current in this circuit. Okay. I am even going to exaggerate a little bit here. I'm going to do the following. To be even more explicit, instead of applying Ohm's law right away, I'm going to remind you that this term here is the electric potential of the resistor. And when we substitute V sub L here, we are going to get, just like before, we're going to get a differential equation of first order. Okay? It's not difficult to solve this equation. That's equal. I'm going to separate the variables. Everything that's I goes to the right, everything that's dt, that's t, go to the left. Okay. Like that. And now what I'm going to do, I'm going to pass this term to the right side. And what else do I have to do? I have to apply an integral to both sides of this equation to find out how the current behaves. and how the current behaves from the instant of time 0 t equal to 0 to t equal to any generic t. Else, here we're going to do the same thing. We are going to integrate for the current between the value of the current at t equal to 0 until the value of the current at t equal to t. L is independent of I, consequently we can take it out of the integral. And we are left with this integral that's easy to solve, right? That's not difficult to solve. And what this integral is going to be? It's going to be the log of v minus ri, minus ri, what else? V minus ri, do I have to put anything else there? I have to put the inverse of r here to ensure to account for this negative and r, right? On the top of that, what else do I have to do? I have to apply the limits. There you don't apply the limits yet. I naught to I. Okay, I naught. I'm not going to apply the limits. Now I don't need the limits anymore, right? The integral on the left side is easy, right? We can just put a t here, and I can simplify this one as well. What is it going to be? It's going to be the ratio something like that. I didn't finish yet, right? I didn't finish yet, but I'm almost there. We're going to pass the resistor to the other side. We're going to divide the resistor by L. I'm going to pass the negative sign to the other side. And then, what else I'm going to do? I'm going to invert the log. Don't forget this V is the potential provided by the battery, right? I want to find the current. That's what I want to find right in here. I want to find this guy. And I'm not done yet. One more step, minus V. And we still have to divide by R. Oh, and I'm going to put a negative sign right in here to get the current. Can you do anything else? Yeah, let's go one step further, right? I'm going to distribute this negative sign. And now we did everything that we could have done. There's nothing else to do, okay? Well, there's one more thing to do, right? We're going to get. We need to find out what I naught is. We still do not know what I naught is. And this I naught we obtain by analyzing the behavior of the inductor, how the inductor behaves, okay? So note that when we turn on, when we close, right? When we close the switch of the circuit, the current builds up from a zero value to a larger value. Because of this dramatic increase in current, will result in a large increase in B, the inductor will work against this increase. It will induce a current that opposes the external current provided by the battery. At the end, okay, this result in an initial current that's going to be zero. Consequently, what we end up having is going to be something that doesn't have the I naught in there. The I naught is going to be zero. And then I can finally simplify my equation. Okay, that's going to be something like that. Okay, I'm going to even put in a different format. Okay, notice that this term here has units of current. Okay, so let's see what happens to this, at time t equal to 0, at time t equal to 0, the above equation will reduce to 0. Okay, for very large equation reduces to what? Reduces to this term disappear, right? So it reduces to V over R. So what has a, this is equivalent to a circuit, to an open circuit, right? To an open circuit. The inductor behaves as though it is a broken wire. Whereas in the second case, the inductor behaves as though it has no resistance whatsoever. Okay? For a small amount of time, for time t equal to 0, the inductor behaves as a broken wire. For very large t, the inductor behaves as though it is a simple wire of resistance 0. Okay, keep that in mind. Okay, so here are the drawings that I have. So here you go, close the circuit, the current will tend to build very quickly. This large buildup in the external current is going to make the inductor to produce a very large magnetic field. But this large increase in the magnetic field will induce a current in the opposite direction. Okay? As a result, the net current is going to be 0 at time t equal to 0. It must be 0. Okay? The induced current is strong enough to counter the external current for the battery, resulting in a net current in a 0 net current at time t equal to 0. Okay, and what else can we say? Okay, not only we say that the inductor prevents the buildup of current, but the inductor also behaves as though it is a battery. We have a concentration of electric charges on this end of the inductor, on the negative charge on the end of the inductor, and a concentration of positive charges in the other end of the inductor. So it is as though at this very instant of time, the inductor behaves as a battery that is working against the main battery. Okay? As time goes by, the current stabilizes. Okay? The current the derivative of the current goes to 0. There will be no induced magnetic field and no induced electric current. T much greater than 0. Okay? So that we can even plot. Here you go. In an RL circuit, what are the, there is a very close parallel between an RL circuit and an RC circuit, okay? So in an RL circuit, at time t equal to 0, the inductor behaves as though there is nothing here as a broken wire, right, in the circuit. The inductor behaves as though it's a broken wire at time t equal to 0. Something like that happens to the capacitor too, but it happens to the capacitor only when t is much greater than Rc. That's the behavior of the capacitor and the inductor. For the inductor, whenever t is much larger than L divided by R, right, then the inductor behaves as though that it is a zero resistance element. And the capacitor also behaves in this way, but it behaves this way when time, not very large t, but for the small t's, right? Small t, for t equal to 0 here, for t equal to 0, tends to V over R, which means the capacitor behaves as a simple wire of resistance 0 as well. See that? It's all switched, right? So it means that what does it mean when we have this type of behavior? One do one thing at time t equal to 0, whereas the other do something else at time t equal to 0. Okay? One do one thing at very large amounts of time, while the other device does something else at very large amount, where the other device does something else at very large amount of times. What does it mean? Okay? Well, it means that those two devices are complementary to each other. That's what it means. It's a device that can be used to make operations. Okay, and we are going to talk more about that once we go further down. Okay, but for now, I want to stop right in here, and we will continue in another recording. Okay, what I want to do, what we did right now is like what we call the charging of an inductor, but then what we're going to do next time, we're going to do the discharging of the inductor as well. Okay, by the same token, we have a charging capacitor, we can also have a charging inductor. By the same token, you have a discharging capacitor, we can have also a discharging inductor. And here you go. When we connect right here, the inductor charges. When we connect on the other end here, we exclude the battery from the circuit. The inductor discharges through the resistor. We're going to do that next time. So I see you in the next recording. Bye bye.